Alright, let's continue on the double integrals. We'll finish one type of question, double integral, and then we'll get on to the concept, so-called applications of double integral. So look at where do we use double integrals for, right? So here's the last type of examples I want to cover for double integral. Basically, how do we deal with a situation like this? It's more or less like the type of question we have exercised in the end of the previous lecture. So here's one situation. Basically, if you have a region R, okay? So here's the region R. And region R is clearly consists of two regions. So you have R1 and you have R2. Very much like in the question in the previous lecture. So you have a diamond, and you can literally separate the diamond into two triangles. Okay. So if this is a type of region, then when you do the double integral over this region R, then you can use this as so-called basically integrate by pieces. Okay. Essentially integrate separately R1 first and R2. Okay. So that's the type of question. There's actually very often, because sometimes your region R is not just ideally, a circle or just a rectangle. It consists of multiple regions. Then we have to integrate each regions, over each regions first, and add them together here. So that's what we call additive property. So additive property here. So I'll show you an example of additive property. So let's say we have a region R which is bounded by three curves: y equal to 2x, y equal to 1/2 x, and then x plus y equal to 2. X plus y equal to 2. Three curves, three lines. If I plot it out, y equal to 2x somewhere over here, y equal to 1/2 x somewhere over here, x plus y equal to 2, so that will be 2 here and 2 here, and then that will be this one here. So this is y equal to 2x, y equal to 1/2 x, and then here is x plus y equal to 2. Okay, that's the region, right? So you have a triangular region in here. So for this region, if I'm going to integrate, let's say, a certain function, we don't have to plug in any specific function here. Let's say we're going to integrate a certain function over this region R and here. Okay. First step is always determine the order. So suppose I'm going to do dy dx as the order of integration. Yeah. Okay, once we determine the order, according to our procedures, is to find the limits for y and x. So if you look at this current region, then according to our procedure, we're going to draw arrow lines in the y-axis direction, right, to find the y mean, y max. Okay. So if as you can notice now, if I draw this arrow lines over here, then my y mean apparently is 1/2 x falls onto this boundary. Y max falls on the second contact, falls onto this y equal to 2x, right? But if I draw it over here, okay, y mean still fall onto this 1/2 x, but then second contact fall onto this y equal to 2 minus x now, right? So apparently, depends on where this arrow line is drawn, then your y max is actually different. Okay? Then, which means you actually cannot just integrate this one in one shot, because you have a two different y max at here. Okay? So, as a matter of fact, you can see that you can separate this region R, okay, into two regions if you draw a vertical line at this intersection point. Okay. So basically you have a R1 and then an R2 over here. Right. There are two regions you should deal with, okay, to find the associated x, y limits. Okay. Let's do that. So now that's how we separate this thing into two regions, and we're going to do R1 first, and then we do R2. Okay. So after you're able to separate these two, then the rest of the job is actually pretty much just the same as you're integrating, through an individual region here. Okay. All we need to do is basically to find the limits. Now, to finding the limits at here, in this particular case, most probably you're going to have to try to find intersection points, okay, between these lines at here. Okay. So let's say, for example, right? Let's take a look at region R1, which is this triangle here. If I go to find the y limits, draw an arrow line in the y-axis direction, then y mean is 1/2 x, y max is 2x, right? That's second contact point. And then we sweep this arrow line, right, from one end to the other edge. So to the other edge is basically the intersection boundary between the two regions here, to find x mean and x max. And if x mean is pretty simple, so 0, and x max, right, is right at this intersection point. So we need to find an intersection point between the two lines. Okay, so let's maybe make a separate, basically, equation here. So one boundary is x plus y equal to 2. The other is y equal to 2x. Okay, so we're trying to solve for the intersection points, right, between these two lines. It's a very simple set of equation in here. So you can get your, let's call this as a point A at here. Okay, so we get a solution for point A coordinates, okay, which is actually 2/3 and 4/3. Okay, so if you solve this set of equation, you get A point with 2/3 and 4/3. So x coordinates is 2/3. Then basically your x max is 2/3. Okay, so that's how you can get the limits for the first integral. And for the second integral, which is R2, very similar. So you draw an arrow line, okay, in the y-axis direction. First contact give you y mean. Hang a second here. Oh yeah, that's right. Then here is 1/2 x. Second contact, okay, give you the y max. That's on this line here. So this 2 minus x. And then move this arrow line from one edge to the other edge. So one edge is actually the end of the previous region. So that's 2/3 up to this point. Let's call this is point B. So we need to know the coordinates of the point B at here. And point B is intersection between y equal to 1/2 x and x plus y equal to 2. So you can try to solve y equal to 1/2 x and x plus y equal to 2. So that gives me point B, which is 4/3 to 2/3. Okay. So the x coordinates for point B is 4/3. Okay. So that's basically the end of the setup for this double integral, and you find all the limits. If we have this function, then you can just proceed and to do the integrals, right, for each one of these separately. Okay. So it's not very bad. Okay. The only trick here is to identify the two regions appropriately. Okay. And then you can identify the limits. Okay. Any question on this kind of question here? Yeah. So now, as a matter of fact, and if you call the end of the lecture, we learned a technique called change of variable, right? Yeah. So change of variable, basically, the idea is to transform the regional sort of irregular type of region into a more nicer region, basically, right? Nicer region, it means a region that can make you easily to find the limits for the integrals. Okay. So for this region, you can actually try this change of variable too. Okay. So I'll give you some hints here, and then you can try yourself. So you could use change of variable technique. So change of variable basically means you have to transform this region into a simpler region here. Okay? And here is the current region. So you have x plus y equal to 2, y equal to 2x, y equal to 1/2, three boundaries here. Okay, 3 boundaries. Yeah. Now I'm gonna use a change of variable technique. I'm going to do this. I'm going to let u equal to x plus y. So basically, I'm going to replace this boundary, right, x plus y equal to 2, with a boundary u equal to 2. Okay, yeah. So instead of using x, y now, I'm going to use a different set of variable now, right, u and v. And I'm letting u equal to x plus y, basically u equal to 2. So let's do that. So this is my first designation. And then I'm going to let v equal to y minus 2x. Okay, v equal to y minus 2x. So what does that mean? Basically, you see this is y equal to 2x here, right? Or it is y minus 2x equal to 0. Okay. So now I'm making a boundary in a completely different, basically, coordinate system, uv. And letting the v equal to y minus 2x, or in other words, v equal to 0, okay, in that uv coordinate system. Okay. So here is the new designation for u and v. Yeah. Then we can solve for the x and y, okay, in terms of u and v based on these two designations here. So solve for x and y in terms of u and v. We get x is 1/3 u minus v, and y is 1/3 2u plus v. Okay. So that's x and y in terms of u and v. Good? Yeah. So, however, the original region R, okay, not only has 2 boundaries, there's what? The third boundary here, okay, the third boundary. So the question here is, I designate this boundary, okay, with u equal to 2 now, and designate this boundary with v equal to 0. So what about this boundary, y equal to 1/2 x, in the new uv coordinate system, right? Yeah. So what you do is basically you look at the three boundaries, right? The three boundaries in UV system. And what do they become? So x plus y equal to 2, as we said, because that becomes u equal to 2. And then y equal to 2x, okay? Given our designation here, becomes v equal to 0. So the question here is that y equal to 1/2 x. Right? What kind of a boundary does it transform to in the UV system? So it's actually quite simple, because given the u and the v as x, y, and y minus 2x, we have solved for x and y here, right? So I'm going to substitute the y over here, okay, with the 1/3 2u plus v, and then substitute the x over here, okay? So basically I get 1/3 2u plus v equal to 1/3 u minus v, okay, for this boundary. So that's the boundary in the UV system. A little bit simplification, so you get rid of 1/3, and you have 2u plus v equal to u minus v, and that gives us a very simple u equal to negative v. Yes. Oh yes, you're right. Yes. Absolutely. Yeah. So I think this is still valid. Yeah. So if you multiply 6 over here, so you get a 2. 2 times this, you get 4u plus 2v equal to u minus v. And u move over here, 3u, 2v over here, negative 3v, so you get a u equal to negative v. Okay? Yeah. Good? Yeah. So now you look at this, the three boundaries, right, in this UV system. You get one of this, and one of this. And how does it look like now? So let's see. If this is my UV system. Okay. So I'm going to draw the three boundaries in the UV system. Number 1, u equal to 2. So let's say 2 is over here. And u equal to 2, that's a perpendicular line, right? U equal to 2. Number 2, v equal to 0. V equal to what's v equal to 0? V equal to 0 is what? That's your u-axis, right? Yeah. And then last one, u equal to negative v, and that's basically a negative 45 degree. Okay. And that's your u equal to negative v at here. So overall, you get a region which is this, okay, in the UV system. So your original R region with this change variable is transformed, okay, into a simple, okay, right triangle in the UV system. So now if I'm going to do the integral, right? If we're going to do the integral, so what do we do? And I'm going to skip the few steps here. You can try to access yourself. You will replace the x, whatever the function. You will replace the x with the function uv. Same thing. You replace the y with function y of uv, and then you're going to have to calculate that determinant of the Jacobian, and then du, dv. The limits for u and v, right? Because this, you don't need any separation in the regions here. If I'm going to do du, dv, all we need to do is, right, you draw an arrow line in the u direction. If I do the du first, right, you draw an arrow line in the u direction. So the u's limit is from negative v to 2, right? and then you go from one edge to the other edge to find the V limits, and that gives you -2 at here for this particular one. So -2 to 0, that's the V limits, right? And these limits are very straightforward. Okay? So then the rest of things, I think if we have the function, then we'll be able to calculate. Okay. So that's the idea of a change of variable here. Okay? I need you to exercise. How do you find this determinant of J? Okay. Given the current function x and y, you had to form that Jacobian matrix, and then you calculate the determinant of the Jacobian matrix. Okay. Yeah. So the change of variable is a really powerful tool, but but oftentimes you gotta identify the boundaries, the new boundaries, okay, new designations appropriately. Any questions on double integral? Okay. So double integral, we have covered Cartesian coordinates. Evaluate double integral using Cartesian. Evaluating double integral using polar coordinates. Okay, and then the properties like what we just covered here, and plus the change of variable approach to evaluate double integral. Okay, so that's all these things about double integral. Let's take a look at a few examples here in terms of applications of a double integral. So we're engineers, you know. We are not only just learning the mass definition of what double integrals are. We really wanted to actually look at the applications of all of these things that we have learned here. Okay. There are really a number of applications here. Let's start from the first very simple one here. If we're given a flat region R, okay, so if we have a region R given, then a natural question could be, what is the area of this region R, right? Now this basically can be done by application of this double integral. An area essentially equal to this. Okay? And in other words, what we're doing here is, so we're letting that function f of x, y that we're integrating with, we're letting it equal to 1. Okay? Equal to 1 here. So then you get integration dA. Okay? So this is very much like this. You know, when you have a single variable integrals, integration of anything. So integrate, if there's just 1 here, then integrate d anything out of here. If whatever you put it over here, okay, you get back to this anything inside the brackets. Okay, so maybe this is x squared, and maybe this is 2x plus 1, whatever you put it into the brackets. Then integration of that d anything give you that anything. So now here it's basically you're integrating this a here, and a here representing the area, right? So dA, if you recall that this is your small area, right? Yeah. So that gives you this area here. Essentially, you're setting this 1 to 1. Okay. Yeah. That's the first application. Yeah. And I think I don't need to really go over any examples here. This is quite straightforward. The second one is also very self-explanatory. Basically, if you're going to find the mass of a thin plate, and this thin plate, okay, has a region R. So the idea is it's a thin plate. It's thin plate, so thin, and then we can neglect the thickness of the plate. So we're basically treating the plates as a flat region R. So if we're going to find the mass, then we have to introduce the idea of a density, right? A density is delta equal to the total mass over a certain unit area. Okay. Whenever you calculate mass, you can use this delta multiplied by the delta A, delta area. Remember, we're neglecting the thickness here, so right? So we don't have a thickness concept. We don't have this area concept here. So the mass density times the delta area give you the small mass, okay, for that small area. And if you add all of them up, you basically get this double integral here. So here's the delta function, and then times dA over the region R, and you get this total mass. Density delta, right, that essentially is a function. So if you look at this one here, this delta here essentially is a function that we're integrating, right? This is equivalent to the symbol f of xy that we have been using. Okay. So here essentially we just replace the function, we call the function f now with a definition of density now. So previously we're just saying integrate this function f over the region R. Right? That's a very mathematical description. And now we can say we're integrating the density over the region R. Then we get the total mass of the region R. Okay. Second, that's the second application. Okay, third application. This is called average value of this function f of xy over this region R. Average value of this guy over region R. So first, let's think about the idea of average. Okay, and you're learning statistics. So if you are given a set of data, okay, if you're given a set of data here, then we can calculate the average, okay, by adding them all up and divided by the total number. Okay, that gives us average. And this is a finite sample here, right? Okay, now I'm going to actually use the same analogy, but this time the average might not look like this average here, but here's the idea, okay? So let's say I have my function z equal to f of xy. So here's my function, which is surface, and then we have our region R, okay, in the xy plane. Okay, so if I pick a point, okay, within this region R, let's say I call this as a coordinate xk, yk. If you substitute x of k, y of k into the surface function, basically you get the corresponding z value, right? So this z value here is z of k equal to f x of k, y of k. And if you look at this thing here, that's basically, I can call this is a height, right? This is from here to here. I represent the height of this at this location. And if I pick another point, and then I get another height. Make sense? Right? So I get it literally, if I pick n number of points, I have n number of heights associated with these points, right? Yeah. So now I can see, okay, can I calculate the average height, right, represented by those perpendicular lines at here. So here's what we want to do, and I say, okay, I'm gonna say height, I call it average height, is equal to, by adding up all of the n number of heights at here. Because if I pick n points, then I get n heights. Divided by n, I get the average height. Straightforward idea, right? Okay. So now I'm going to manipulate this a little bit here. Okay, going to manipulate. How I manipulate this? I'm going to do this. I'm going to consider, as we did in the previous case, I'm going to consider there is a small area, okay, a very small area associated with each one of the points that you have picked within this region R. So around every point there's a small patch, delta A. So that's what delta A is. Then I'm going to multiply the delta A at the bottom of this, at this denominator, but I cannot change this expression, right? And then in order to maintain the equality at here, what do I need to do? I need to multiply delta A, so I maintain the same equality. So now I have this h height, the average height, is in terms of this expression now. Okay, yeah, and that's based on a finite number of selection points in the region R. Then, if I want to get the precise average height, then what do I need to do? Then I need to what? I need to let this n go to infinite, because there are infinite number of points within this region R. Okay? Yeah. So when n goes to infinite, then the delta goes to basically d, and the sigma goes to what? A double integral, because you have two variables here. Okay? And that's the idea. So now your average height, okay, becomes 1 over n times delta A. So guess what? If you have n go to infinite, what does this n times delta A give you? 0? N go to infinite, delta A go to 0. So, but when you multiply these two together, what does delta A here? Delta A is one small patch, right? Exactly. So you get your R, which is you get your area of R here, right? So the n times delta A, as n goes to infinite, it becomes this total area of this region R, right? Because you have so many delta A now, and then you add them together, you get total area. Summation sign becomes the double integral sign. So that's integration over R and then dA here. Okay? Yeah. So that's what this become now, right? Your average height, the accurate calculation of the average height can be done by the double integral and divided by the area at here. Okay. So here h is called the height. Basically, I'm using this graphical idea. That's your function value f at each point. That's the height, right? So basically, this is your average value of this function f. So it doesn't have to be the height concept anymore. You know, I introduced this idea of the average height, but it's really just average value of this f here. So f here is called average value of f over region R. Okay. And you can consider as height, not a problem at all, right? Okay. But I can certainly give this average value f a completely different physical meaning. For example, right? So f not necessarily represents height concept. F maybe represents temperature. Okay, maybe represent temperature over a thin plate. So you have a thin plate at here, and you pick any point on thin plate, which is the region R, and you got a temperature value, and this temperature value spans across this region R, which can be represented with the function f of xy. Then, if you're required to say, then what is the average temperature, right, around this across this region R? So how do we calculate? You use the same formula in here to calculate this average temperature. So F bar here becomes the so-called average temperature. Okay. So that's the point, the so-called this average concept. The average concept of this function F over a region R. Okay, that's a precise calculation using double integral at here. Is that good? Yeah. Okay. So we'll look at examples later. Okay. But let's put down, because some of the examples actually combine some of the applications together here. So that's number 3 application. Number 4 application is called weighted average of function f. Okay, weighted average. And you're learning statistics again. You know, you probably have learned this weighted average. So weighted average basically means, you know, each sample there's a different probability associated with that event or sample, right? So let's say, for example, if I have a data set x1, x2, and up to xn. So there are n number of data. Okay? And there's also a weighting factor associated with each sample. So basically it's like a student grades. The probability of 95 is 0.01, but the probability of 75 probably 0.2. Right, that's the weighting. Okay. Then, if I'm saying, so what is the average of this data set? So what you do is you use the weight times each data set, okay, and then divided by the sum of the total weight. Then you get this x bar is called the weighted average. So this is called weighted average. Okay, yeah. So very simple concept. Weighted average, right, just basically means there are different weights. Now, what if your weight W1 to Wn are equal to each other? Then, let's say when you have 6 number of data here, and then the weight for each one of those is 1/6. So when you plug it here, you'll get back to which one? You get back to this average here, right? Yeah. So this is a general case, the weighted average. So how does that do with our case at here? Okay. So this is what we're going to do. What we're going to basically do is we have a data set, for example. Okay. we have a data set. So let's call it f of x1, y1, and then up to f of xk, yk, okay, and maybe up to n here. Okay, yeah. So we can easily have a data set f of x1, y1, fk, yk, and xn, yn at here. This is basically the idea of the height, right, that we introduced at here. So you have this data set at here, which represents the height, okay, at each point. Good. So now, instead of calculating the average height as we did in the previous application, so now what we're going to do is I'm going to consider the mass concept. I'm going to weight each one of the data here with our weighting at here. Okay, so we're going to weight, giving our weights. So what are going to be the weighting at here? We're going to use the small mass at the location. Okay. So consider we have a small area attached, okay, to that particular point, x1, y1. You use the density multiplied by the small area, then you get the small mass around the area, right? So I'm going to use this as my weight, okay, associated with this particular data point. And similarly, I'm going to use another one here, okay, for that data points. And of course, we have the last one here in general, okay, for that points here. So you got this data set, you got this weighting set. Then I can calculate the average now by applying this formula. So the numerator is the weight times the data point value divided by the summation of the total weight, okay, of all the weights. So if I use a simple mathematical symbol, when I sum this times this plus everything together, so the weight times this is, each one of those is xk, yk times the weight okay, and then divided by the summation of the total weight. So you can, this is k to n, k equal to 1 to n, like this. So if we do this, we get our weighted average, right? We get our weighted average as we have our definition for weighted average for. That makes sense? Yeah? Okay. So if we let n go to infinite, right? If we let our n go to infinite, then we get, what do we get now? This weighted average, okay? On the top, okay, summation sign becomes double integral. So double integral of this function f xy over the region R, density delta xy, and small area becomes dA. So the top becomes this integral here. And the bottom is, if you look at each one of this, which is basically what? The density times small area is the small mass. And then when you add all small mass up, you get the total mass of the thin plates, right? As n go to infinite, then you get precisely this total mass at here. So you get this, the mass of the region R. Okay. So mass of region R, and that's another double integral, so delta times dA here. And that's actually the application number 2, right? That's application number 2 here. Okay. So now you see your weighted average. Okay, so this is weighted average. Is equal to this numerator divided by this denominator. Okay, that's your weighted average. Now delta, I covered the delta, right, with idea of a density, but mathematically delta can be any function, right? You can consider as, so delta xy times dA, it considers just a general weighting function. Not necessarily is always a density, right? And that's the idea of mathematics. And as a matter of fact, okay, if delta equal to 1, so if your density equal to 1, in other words, you have a unified density across the whole thin plate. If this equal to 1, this equal to 1, what does this weighted average become? Exactly, right? Yeah, it becomes this average concept. So F is just the average now. Okay. Good. Okay, so with all this for application, then I'm ready actually to introduce you a few mechanical properties. Okay, that's actually some of the properties you have learned, but more general now in this case, especially after the triple integral. Then we'll have more general concept. Basically, the first one here is called the center of mass. Okay, and then we'll look at moment inertia. Okay. Center of mass is a concept, basically, if I have a thin plate, for example, represented by a region R, okay, and you want to find a point, okay, on that region R or on that thin plate, and this point representing using y bar, x bar, y bar, okay, and we call this as a center of mass. Sometimes we call it centroid. So x bar, y bar, okay, is called, okay, center of mass. So then how do we find the center of mass then, right? How do we find the center of mass? Center of mass essentially is it's an average concept, right? It's an average concept. We learned from application number 4, weighted average of function f. So we can actually directly make use of the conclusion and here, the results that are here, to get this average value x bar. Because why? So we let our function f of x y equal to x. Okay? So as simple as that. If we let our function f equal to x, and guess what? If we look at this expression right here, then this becomes the x bar right here. So that becomes basically the average x value, right? So then we get essentially x bar equal to 1 over the total mass, and then x times a weighting function, and dx dy or dy dx. Okay. So that gives us this average value, right, for this x bar here. It's a weighted average for starters because the plates very probably have an uneven distribution of density. Okay. Similarly, if we let our function f equal to y, then we get our y bar equal to 1 over mass y times delta xy dx dy. Okay, that makes sense? Yeah. To further give you a little bit of understanding of this average value x bar, or the center mass at here. So what exactly actually does it tell you is, I want you to focus on, let's say, focus on the first one here, okay? Focus on the first x bar at here. So x bar equal to this whole expression. Okay. Now, if I multiply the mass over to the left side at here, so what am I going to get? I get, let's say, I'll call this m equal to the mass. Okay. So I'm going to get what? M times x bar, right? M times x bar, and equal to, okay, equal to the total summation here, and then x times delta xy. Now this time I'm going to use the dA at here, okay? dx dy, I'm going to use dA. So that's what we're going to get if we move this mass over to the left side. Okay. Yeah. So let me redraw this diagram here. So here's region R. Okay? Yeah. Let's say this is your x bar here. Okay. So what is x bar? X bar is which distance? It's the distance from here to where? If this point has x bar, y bar, x bar represents a distance from this point to which axis? To y-axis. Right? Yeah. This is your x bar here, right? Okay. Yeah. Then what does m times x bar mean? So I'm going to give it a physical meaning at here. I'm going to call it mass moment. You learn moment, right? What's moment? Moment is equal to what times what? Force times distance, right? So that's called force moment. So this time I'm going to call it mass moment. Is it okay? Right? It's actually okay. Okay. So I'm going to call this as a mass moment. And this is the mass moment representing the m is the total mass, right? And x bar is the average value, is the center mass. So this is a mass moment about the y-axis, because times x bar. That makes sense, right? So, and I want you to tell me back to the force moment thing. If you only have one force, how do you calculate moment? You calculate force times the distance, right? But if you have a multiple forces applied to the object, and you want to calculate the total moment about certain axis or point, how do you calculate? For times each individual distances, right? And you add them up, you got a total moment. Okay? Now I'm going to go back to this. This is my mass moment. I'm going to look at the right side here now. Look at the right side. What is this guy here? That's a small mass, isn't it, right? That's a small mass. So if I have a small mass at here, delta m, if I ask you, what is the mass moment for that small mass? What do you do about the y-axis? You use the delta m and then times what? Times this distance here, right? So let's call this x at here. Okay? So if I have another small mass and then times another x here. So now the question, if I ask you, what's the total mass moment? What do? You add them up. When you add them up, mathematically it means double integration here. So now you see, you look at the left side here, at the right side here, that's basically a summation of individual mass moment, okay, across this region R. And when you add them up, you get the total mass times the center of the mass. You get a total mass moments, basically. Okay? Yeah. And this is actually legitimate definition, mass moment here. Okay? Yeah. And actually, we have also a concept called area moment, as we're going to see next. So that's kind of give you an idea of basically what does the center of mass means. How do you get the definition in here? Yeah. As a matter of fact, we can let my equal to the right side at here. I can let my equal to this, and also I can let mx equal to the other one for the y bar. Okay, so I can define basically two new symbols. I call it my and mx. Okay, yeah. And these two, okay, there's a name in here. This is not necessary for this course, but if you are in mechanical or mechanics material, and this is so-called the first moment, okay, of the area. The first moment of the area. Okay. We can consider the area basically as a cross-section of a solid. Okay, a cross-section solid here. So if you cut a solid, you always got a cross-section. You got to get a cross-section area. Okay. My here is respect to y-axis, and mx here is respect to the x-axis. So these two, right, are the so-called first moment area respect to the y-axis and x-axis respectively. Okay. In terms of computation, you don't have to worry too much about the definition later, but I think it's helpful to give you some of this definition here. You may actually come across in the future courses. If you see that kind of definition, you probably will jog your mind. Oh, right, I think I have actually learned that. But in terms of computation later, right? This is just a pure double integral computation. So that's mathematically there's no mystery at here. Okay. Okay, so that's number 5, mass center for mass application. Okay. And the last application is moment of inertia application. Now this time it's not a moment inertia of 3D objects. We're talking about actually 2D plates or thin plates. So more precisely, we're talking about moment inertia of the area. And this is actually, if you search it up, a different name is called second moment of area. Okay, second moment of area. So you might wonder, why is it called a second moment area? Because here we have a first moment area, right? We have first moment area. So first moment area is here is you have a dA times something, so times the distance. As you're going to see next, you'll see why it's called a second moment of area. Okay, so I'm going to go over this very, very simple concept here. Okay, it's not a dynamics course. So first, okay, let's look at some of the basic concepts here. So what is mass? As in your high school physics probably learned, mass is how hard it is to impart translational motion. Okay, so you have a huge mass. So what does that mean? It means it's very hard to impart a translational motion. I guess what law is that? That's Newton's first law, right? Yeah. And what about moment of inertia now? Well, a moment inertia is always about an axis, okay? Okay, so what about moment inertia? Can you use a similar description to the mass to give an explanation, simple explanation for moment of inertia? So if your mass is how hard it is to impart translational motion, then what about moment inertia? How hard it is to impart what type? Rotational type of motion, right? So that's what basically moment inertia is. Okay. And moment inertia about a certain x, so we always try to be accurate. So it's a rotational motion about certain axis. Okay. So let's derive the moment inertia here from very simple concept at here. Okay. Yeah. So let's say I have starting from a point mass. So here's a point mass, m. So very small mass is called point mass. Point mass basically meaning it's a small point that you don't consider rotational about its own body, basically. Okay. Yeah. So let's say so this point mass right now is going through kind of a motion like this, okay, and it's moving in that direction, okay, with a velocity v, and it's trying to move around that particular curve like that. So I can use polar coordinates here. I call this is r. Okay, I call this r here. Okay. Suppose that this point mass, okay, moved in that direction v, and moved away, okay, with a very small angle delta theta. So as I move over here along the trajectory, it yields a very small angle delta theta in delta t amount of time. Okay, so in delta t, we yield a delta theta angle of difference. So now I can start to calculate things based on these given parameters. So let's say forget about vector first. Let's just focus on the speed. Okay, focus on the speed here. If I'm going to ask you, can you give me an approximated speed, okay, for this point mass due to this motion? So the motion basically means from here to here, delta t time with a delta theta change. So speed basically is a delta s over delta t, right? It's the small displacement over the amount of time delta t. So now if you look at this current description from here to here, even though this is not a straight line, but because if it's delta theta is small, so I can consider this is a very much a straight line at here. Then what is the amount of a displacement from here to here then? It's what? I can consider it from here to here as part of the circle with a radius of r at here, right? Then this arc length will be r times delta theta. Okay. So now you have your displacement, you have your amount of time, so you get your velocity, you get your speed v. And if we let this delta go to really small, differential small, so your v becomes r times d theta over dt. Okay, so that's a connection between your linear velocity v and the angular angle change theta, rate of change theta. And d theta over dt, okay, as we have learned, we can use a symbol omega. Right? d theta over dt basically is called the angular speed, omega. Okay, so essentially we get a conclusion v between v and omega, v equal to r times omega. You learn that in the dynamics, okay, or kinematics. Okay. So now let's go back to the kinematic, the kinetic dynamic, the kinetic energy. Okay, kinetic energy. Kinetic energy for this point mass at that point, okay, is equal to 1/2 m times the speed square. Okay, that's your kinetic energy. And I have just derived the v at here, so I'm going to replace the v with r omega square. Okay. And then I'm going to manipulate this just slightly. Okay, I'm going to r square omega squared here, so m r square omega squared. So separate this. Okay, separate this out. And also, I'm going to let mr square, okay, as a single quantity. So we're going to let r I naught equal to mr square. Okay. Yeah. So what happens that here is you have a mass times the distance r squared, and the r is the distance from the mass, the point mass, to origin. Okay, to the origin here. So this guy here, okay, is actually defined as the so-called moment of inertia, okay, of this point, okay, about an axis, okay, about an axis through origin. Okay. So I'm writing all of this detail because moment inertia is always about an axis. An axis is always about somewhere through certain points. So that's called moment inertia for point mass. So you see the point mass here. It's m times r squared. Remember that in the previous application, when I have a m times the distance, what do we call that? We call that what? Mass moment, right? Mass moment. And we also call that first moment something, right? Later. So this part, I have a title here, is called second moment. Why is it called second? Because of this m times r squared, instead of this m times r as in the previous case. Okay, that's why it is called second. Okay. As a matter of fact, you probably say, is there a third moment? Yes. Is there a fourth moment? Yes. Is there any moment? That's actually yes, right? So there are mathematically, you can go any higher. Yeah. Now, if you go back search, okay. Anyway, so it's too much. I don't want to confuse things. Yeah. So anyway, so let's come back to here. So kinetic energy, coming to using 1/2 using the I here. So I naught times omega squared. Right. So this your Ke can be expressed with 1/2 I naught omega squared. So that's kinetic energy for a single point mass. Okay, either you use the linear velocity, or you can use this angular velocity, right? Yeah, but the expression is quite different, right? Yeah. Okay. So now let's extend it to a solid here. So how about a solid with density delta? Okay. So if I have a thin plate R, which has a density delta function, then what will be the moment inertia of this thin plate on an object? So like this. So here's a region R here with a delta density distribution. Okay. So then what will be the moment inertia of this object about an axis going through this origin here? So in 3D space, I should probably use better. So if I have a region R, and this is XY plane, this is your Z plane here, you have a delta function distribution across the region R, then what will be the moment inertia of the thin plate about this Z axis here? So that's the point. Okay. So what will be the moment inertia of this region R about Z axis? Okay. Yeah. That's the general, right? We're going to basically easily derive from the point mass. So if you have point mass, that's point mass with respect to the z-axis, which is this, okay, mr squared. So what about a region R now? And we can easily extend that by doing this. I can pick a small mass, okay, anywhere within this region R. Let's call this delta m. And then delta m, okay, is equal to basically the density at that location times the small area delta A. So this is your delta m equal to the density at that location times the delta area. So the question is, then what is the moment inertia of this small mass about the z-axis then, right? So that's easy. We can consider this small area as the point mass. So then your moment inertia, okay, is delta m times r. Let's call this rk here. Times rk squared, okay? Or is equal to rk squared times delta A. That's point mass. Basically, that's the definition of a moment inertia for point mass, right? But if I'm looking for is the moment inertia of the whole region R, then all I need to do is I'm going to add all of this up to give me the total moment inertia, right? Because those are individual here. And when you add them up, you get basically this double integral here. And you get r squared here times delta times dA and over this total region R. So basically you add it up, we get the following expression, double integral. And that is the moment inertia of the thin plate with respect to the z-axis, which is goes through this origin here. Now r at here, okay, what's the r? So if you pick any point and up to here, that's your r, okay? If this point has the coordinates x and y, then r basically is x squared plus y squared, right? That's the distance from that point to the origin O. So the r here basically is x squared plus y squared. And then x delta is certain function that should be given by the question. Okay? Yeah. So overall, we have our moment inertia I here, and often in time, this I here, I should probably say, sometimes the I here use a symbol J. Okay? Instead of using I, you use a symbol J. Because why? Because this is about moment inertia about the z-axis, okay, which is basically about the origin, about the z-axis going through the origin in here. So this one here, often in time, is called polar moment of inertia. Okay, so polar moment inertia. So it's about that. It's a kind of special, basically, moment inertia here. Okay? It's not arbitrary axis, basically. Is that good? Yeah. So, in terms of computation, I'll give you an example in the next lecture. But if you look at this one here, you know, if I just present this to you as a double integral, there's no difference from any other double integral, right? Yeah. But it does have a special meaning in here. So we'll look at a couple of examples in the next lecture. And then that should be it. Okay? Any questions so far? Okay, thank you.